a PhD degree from Indian Institute of Information Technology, Kanpur. His research area, quantum optics, quantum information theory, and non-linear dynamics. Professor Babu, please continue.
Yeah, okay, thank you, Dr. Rajivaria, for the introduction. So I just want to check if the session is being recorded.
Just
sir, session will be recorded. Yeah, hello.
Recorded.
Session will be recorded.
Oh, great. Okay. Fine. Okay, that's nice.
This will go into YouTube also, sir, today evening itself, like how we were sharing Nivedita ma'am's lectures, right? And later we will curate this and place it in the one of the either in Swayam or NPTEL, right?
Okay. Right.
Sure.
So yeah, so here, so let me start.
Sure, sir. You can start.
Yeah. So yeah, once again, very good afternoon to all of you. I hope you can see me as well as my hand notes. Just set it up. So let's see. I hope, yeah, you guys can see my hand notes and also hear me loud and clear. Okay. Yeah, let's do the session slightly different from what is being done so far. Okay. So yeah, very good afternoon to all of you. So the things are, this is how I'll do it. So I'll just use my hand note most of the time. Okay. And I will give the running, like I will be writing, and just like a classroom teaching, I'll be writing everything and explaining things. Okay. And the same at the end of the session, I would also share my proper hand notes, not the running notes. And proper hand notes I will share, which you can go through and read through and understand. And also I'll share whatever I have explained on the board, whiteboard. Okay. So this notepad platform, whatever I write, that also I'll share. So in that way, both will be shared to you. And I urge to all the participants, please pay attention. There is no need to write anything for yourself with your running note or anywhere. If you find something very important which I said, those things you can note it somewhere on a notebook somewhere or a scribble somewhere. But whatever I say, like 95% of the things would be given in my hand note as well as my classroom note. Okay, fine. So yeah, with regards to the doubts, so I just request all the participants, please make the questions or give the put the questions in the chat which are related to the content which is being discussed. Okay, I'm not denying the questions beyond this content, whatever I going to describe today. You can also pose the questions beyond this, but as of now I can't explain or answer them because I would be going through the flow of this particular content which I'm explaining for today. So those questions would definitely, we can have it probably after the session or somewhere along the way in this week. That is the idea. Okay, so I'll try my very best to explain whatever the knowledge which I have with regards to the quantum sensing as well as quantum computing, since I'm working in this field for the past 8 to 10 years. So I strongly feel that I could try myself to answer the questions whatever you have. Okay, right? So yeah, so those are the preliminaries we would set up. You can just since you can't unmute yourself and ask, you can put in the messages on the chat. I would be saying now and then. That is how we'll do. We give a break exactly at 1 hour. Okay, for 5 minutes we'll give a break and then come back and restart the session. Okay, fine. So I will make a simple and more informative rather than give lots of information. I'll go very slow. Hope you would get. Okay, fine. So I would start. Now you can see in the title itself, quantum sensing. So I was given 5 days. Okay, 5 days with 2 lectures each. okay, to cover content related to quantum sensing. So here, some of the subtopics which I was supposed to discuss is the basics of quantum sensing. Okay. Number 2 is the basics of, for quantum sensing, we would be needing single photon source, basics of single, and also entangled, okay, photon sources. Their basics I was asked to introduce or teach you. And there is some of the specific quantum sensing technique called gravitometry or gravimetry. Okay. Number 4 is atomic clocks. So it's another way of sensing. Okay. And number 5 is magnetometry. So basically sensing a magnetic field using quantum systems is a magnetometry. I was asked to discuss that also. And then finally, the state of the art of all the sensing techniques. Okay. So I am thinking to divide this entire topics among these 5 days, whichever I was thinking about. So today I would discuss this today, right? I'm hoping I'll finish this today. If some part is left, so we'll go for tomorrow and tomorrow also. Okay. And after that, the remaining part, we would start the basics of single and entangled photon sources. Okay. I'm hoping tomorrow or day after, if not possible. Tomorrow, I'll go for day after. And then gravitometry and atomic clocks could be 1 day session, 2 hour session. Okay. And magnetometry itself would need 1 day. Definitely, it's a very large and a huge field. Okay. On the final day, I would discuss the state of the art of all the quantum sensing techniques. Okay. So this would be on Friday. So I would be needing the 5 days of in sessions. Okay. 2 hours each in each given day. Okay. So this is what I want to discuss. This is what my plan is. Okay. So let me go further now. Fine. So to start with this first part, the basics of quantum sensing, we would be needing few things. Okay. Right. So those things, let's straight away get it. And then we will get into the understanding of quantum sensing. Okay. The first thing I would be needing for a quantum sensing is, okay, some system which is allows us to sense. Okay. Right. So the first thing which comes under quantum computing or anything which could be used for sensing, let's say take a qubit. Okay, so you people are all comfortable with a qubit. Let me write a qubit. Qubit could be, okay, you all know qubit could be photonic, means energy based, or material based, or atomic or anything. It can be neutral particles, neutral atom, or anything, or any other form. Okay, right? So these are the basic ways I can realize of qubit. Let me write on the paper mathematically what it is. So you guys know quantum state is, usually I'll write as alpha 0 ket plus beta 1 ket. Okay. So this is a quantum state for you. Fine. Now this is I want to use to do the sensing. Okay. So it's like a probe which allows me to sense. So the best classical example, okay, let's go for a classical understanding. Classical understanding what we have. Okay. For example, a patient is having a fever. How do I check? I'll use a thermometer. Okay. Right. Or thermal gun these days, or even the doctors can touch and feel the temperature of the person. So here thermometer is a probe which allows me to check the temperature of the patient. Okay. Similarly, I want to sense something. So I need a probe. So qubit is my probe. Okay. Fine. Here the thermometer, it has got a mercury, and as it feels the temperature, when the thermometer is put close to a person, depending on the temperature of the person, the mercury would enlarge, and it shows some enlarging. Based on that, I would get some 101 degree Fahrenheit or 99 degrees Fahrenheit. Like that, I would get the temperature. Okay, fine. So here I have a probe. A probe has to go through some changes. It has to undergo some changes. Based on what is the change it is undergoing, I would sense. Okay, so I want to understand how this how this change could happen. Okay, now since I'm talking in terms of change, let me construct the change in time. Okay, so let's say quantum state in general is a time dependent, it evolves in time. So in that case, probability amplitude also becomes time dependent. Okay, fine. So now it's a time dependent form I have. Fine. So this would go in the vicinity of some field or something, it undergoes some change. Okay, hopefully you might have got some introduction to the change of a quantum state. So usually the quantum states goes through some gates and evolves with some change. Okay, so where the transformation is a unitary transformation. Okay, so just for the clarity, some of them were starting very early stage. For them, let me tell what is this unitary transformation is. Okay, so basically this is a column vector, and this is also column vector. Let's say if it is alpha beta, this is alpha prime beta prime. So basically the change going from here to here is happening through some gate, which is actually a matrix, a transformation matrix. Okay, right? A transformation matrix acts on this. Okay, and it gives us this. So that is what the transformation, that is what the unitary transformation is. Now let's say we have a quantum state at time 0, okay, which undergoes some transformation, some gate, and gives us the quantum state at some time t. This is what I get. Now, how do I explain that or describe on the paper? Okay, mathematically. So which would be simply psi of the new state would be equal to some matrix, U matrix, which connects system from 0 to t. Okay, the old state. I'm sorry, old state. This is what the mathematical representation of transformation. Now, let's say I don't know what is this. I don't know. Okay, I want to find out what is that. Now, let's remember, this is the transformation matrix, which is causing changes in this quantum state. Okay, so that means the quantum state is surrounded by some environment. Okay, some environment is there. Environment. Okay, so environment means atom is, let's say, one single atom is surrounded by some environment, or a photon which is in an optical cavity. So that is undergoing some change. So basically this U should carry the information. Okay, you should carry the information of surrounding, carry information, okay, of the environment. Fine. So
Sir, sorry for disturbing. Sir, some people are comments here. Your voice is not clear.
okay, my voice is not clear. Okay. Yeah. It is clear. Somebody is saying it's clear. Okay. Yeah, it's clear. Most of the people are saying clear. I'm just sitting very, very close to my mic. Okay. So.
Okay, sir. Sorry for disturbing, sir. Okay,
Yeah, it's okay. It's okay. You can cross check. Yeah. Okay. So now, unitary transformation is there. Or some matrix is there. Right now, let's say I will not even say unitary transformation. Some transformation matrix which U does some change to quantum state and which gives me the new state. Okay. Now I want to know what is that U state is. Okay. So right now the simplest way I can describe the environment is, let's say it is the atom is surrounded by some environment. First of all, I should know how to represent the atom as such. Okay, so in general, atom is actually having, let's say, two-level atomic system. If I just take, it's a ground state and the excited state. Okay, basically always people use 0 and 1, one horizontal line, one vertical line, one horizontal line. What it means is, if I just take a nucleus, okay, it is surrounded by orbits. Okay, so let's say this is 0th orbit, this is first orbit. So I'll just take a snapshot of this part. That is what I am writing here. Okay, right? Now let's say the electron is in the ground state. If I supply the energy, it will go to the excited state. If I supply a photon, okay, after some time it cannot stay back and it will just deteriorate back to the ground, and it will send the photon energy which has consumed. Okay, right? So let's say this is the scenario when atom gets interact with the photon. Fine, let me write down when there is no photon is there. Okay, and what would be the representation of atom, okay, using some matrix form. Okay, so which is in general, let's say the ground state is having energy A0, excited state is having 1. Okay, right? So then the system is described by something called energy matrix. Okay, energy matrix, or Hamiltonian, a fancy name, Hamiltonian. Okay, so which would be Hamiltonian would be equal to, right? So it will have a ground state energy E0 and excited state energy. Okay, and it is also written in terms of E0, outer product of 0 with the 0, plus E1, outer product of 1 with the 1. Okay, so you might have seen inner product. Inner product means, the inner product means break comes first, get comes later. This is the outer product. This gives me a matrix. Okay, we will see that. Okay, so now I have a matrix. Let's say there is no environment, the system is there, which is explained by H matrix. Okay, now whenever there is a matrix is there, a system is ideal, not interacting with any environment. The matrix is, sorry, some state is there, Hamiltonian system described by. That means it can exist in some energy states, eigenstates. Okay, eigenstates, and also each state will have some eigenvalues. Just like any matrix possesses eigenstates and eigenvalues. Here the Hamiltonian would describe, I'm sorry, here Hamiltonian would describe the quantum state, the atomic state could exist in either 0 form or 1 form. Okay, where energy of 0 is E0 and E1. So just mathematics, I just bring in mathematics and describe that as an eigenvalue equation. Eigenvalue equation. Okay, so eigenvalue equation would be H acting on some quantum state is equal to each one state would exist with some eigen energy. So this is correspond to E. E, capital E I am writing, capital E could be E0 or E1. Accordingly, the quantum state psi would change. Okay, right? Right? So accordingly, quantum state would change. Now, in quantum physics or quantum mechanics, right? So whenever I put a hat on a label, which means it is in the operator form. Okay, operator form means it's not just a number, it becomes some kind of operation on something. So basically the E is operating on quantum state. It is operating. Even H is operating on psi. So basically this, whatever eigenvalue equation I have written, this is actually Schrodinger equation. Okay, right? So why did I bring this here? Because this Schrodinger equation would allow me to find the dynamics or dynamical evolution of this, dynamical evolution of a quantum state. It allows me to find how this evolves. Okay, so if you are still not getting what I mean, let's get back to the classical analog. Okay, let's classical analog. That is the easiest way to understand what I want. Suppose a particle, a box is there. Okay, somebody puts a force on the box, which is on the floor. Box has a mass, m. Okay, a box, somebody is putting a force in this direction, so box would move. Okay, so box would move with some acceleration a along this direction. So force is along the towards the right, and mass would move. So I explain this process by using force acting on a box is equal to mass into acceleration created by the force. This is Newton's second law. Okay, Newton's, right? Now, by solving this equation, there is nothing to solve here, you might say, but there is something. So acceleration means what? Rate of change of velocity, which is what is the rate of, what is the velocity? Velocity is rate of change of position. Okay, so basically acceleration is second derivative of position. Okay, so second derivative of position is equal to, okay, so the mass into acceleration is equal to f, right? If I divide it by f1 m on both sides, so I'll get rid of mass, so I will be getting second order differential equation. Okay, by solving this second order differential equation, solving implies the position of a particle at every time t I would get, and also its velocity at every time I would get. Okay, solving gives you that. So what I'm doing is I take a Newton's second law and solve it to know the system, how it is evolving in time when external interaction is put. So same thing here. A quantum state would undergo some external intervention, and it is going through some evaluation that I want to know. Okay, so for that, a Schrodinger equation is just like a Newton's second law. In fact, it is connected or inferred from the Newton's second law. Okay, in quantum mechanics or quantum physics. Okay, this is at quantum regime, means atomic or subatomic level. Atomic or subatomic level. So at that level, I need Schrodinger equation. Now let's write the Schrodinger equation. Okay, Schrodinger equation. I'm just writing like this. Okay. Now, let's say psi is time dependent. Okay. So in quantum mechanics, there is some very tricky thing. Okay. What is that is every operator would take, this is observable, or it can also called as operator. Operator would take operational form. Okay, what I mean is, interestingly, H can take, H is what? Hamiltonian, na? Hamiltonian, which is equal to total energy function. Usually it is written as a kinetic energy operator plus potential energy operator. Okay, and energy itself, what is there on the right, would take an operator form, which is I H cross dou by dou t. Okay, this is operator form. Whatever comes on the right, if I say E acting on psi, which is, if the psi is time dependent, is equal to I H cross dou by dou t psi of t. Okay, so this is what the operator form. Now, straight away I gave you this equation. Okay, I took it for granted that you guys know. If somebody have a doubt, let me describe what it is. Okay, now let's get back to some very basics. I just want to clear the basics. What is that is, suppose if you just take electromagnetic wave, which I have written as EM wave. Okay, E is equal to exponential I into, okay, K dot R minus omega t. Okay, so this is electromagnetic wave which is going along the propagation vector R, and in 3 dimension is going. Okay, so this is electromagnetic wave or electric field oscillating, and there is a magnetic field also. Similarly, magnetic field also there with the same kind of a phase factor. This is a phase factor, which would be if this is oscillating in the vertical plane, the electric field. Okay, in the horizontal plane, magnetic field would be oscillating. Horizontal plane. All right. So electric field would be in the vertical plane. Now the wave means I just gave a nice sinusoidal curve wave, nice sinusoidal. Right. Fine. So probably you might have got some intuition about quantum physics by now, right? So that is quantum states are quantum particles, let's say atom, are photons, both are qubits. Okay, they exhibute dual nature, duality. Duality means what? A particle would behave like a wave. Particle being material behaves wave nature, and photon, which is the energy, shows particle nature. Okay, both are there. So that is what the duality is for you. That means the atom or a photon which I represent by qubit would also be represented by some quantum function, wave function. Okay, right, just a minute. A wave function which I am going to represent as quantum function, a wave function. Psi of r is equal to exponential I k dot r minus omega t. Just like electromagnetic wave, I represented quantum state as a wave function, just like a wave like that. Now the question is, what is the amplitude? I have amplitude for the electric field. Okay, right? So this is the way. So there is no amplitude here. Amplitude means what? The strength would be given for electric field. Similarly, the amplitude for the quantum state is actually 1 because it's a unit vector. So I don't have any constant here. I just have 1. Now let's take quantum state represented by a wave function like this. Okay. Now it evolves. Let's say it is time dependent also. I forgot to put it's time dependent. Now let's say it's evolving in space or it's moving in space, and also it is evolving in time. So if it is evolving in time means I want to know how it is changing in time. So let's take a time derivative of psi. Okay, which is equal to, so its exponential function is there. I can straight away exponential derivative of exponential is as it is plus derivative of the phase term. Okay, so here the first part is time independent, second part is time dependent. So I'll have is equal to, okay, minus I omega t. Okay, so what I'll get, I omega exponential I k dot r minus omega t. Okay, so what I am getting, the time derivative of quantum state is equal to minus omega, and the state itself, let me write that as it is, derivative of quantum state is equal to minus I omega, the quantum state as it is. Okay, right? What it is conveying is, okay, taking a derivative is nothing but multiplying the wave function by some factor. Now, for a photon, what is the energy? Energy of photon is h mu. Multiply and divided by 2 pi. So what I will get, energy is equal to h cross, h by 2 pi is h cut into omega. 2 pi mu is omega. So energy is equal to Planck's constant, scaled Planck's constant multiplied by angular frequency, where omega is h e by h cut. So let's replace that here. What I'll get is, let me replace equal to I e by h cut into quantum state. Okay. Now what I'll do, let me send this negative minus I, complex I, and h to the other side. Let me write down that E psi r comma t is equal to, okay, if it goes onto the left side, it becomes IH cross dou by dou t psi r comma t. Okay. Now, if you can carefully see, a acting operator on a quantum state multiplied by some factors of I and H cross is nothing but multiplying the quantum state with some energy. So that is what the operator form we have. So remember, the operator form for the energy is IH cross dou by dou t. Okay, that is what I wrote earlier. Similarly, you can have operator for even momentum operator, linear momentum operator, which is minus IH cross dou by dou x. Remember this. Okay, so similarly, you can derive operator form. This is a linear momentum. Remember, linear momentum operator. Okay, so which is actually important when it comes to describing kinetic energy of the quantum state, which is involved in the kinetic energy of Hamiltonian. Okay, so let me get back to this part. Energy eigenvalue equation, which is eigenvalue equation. Okay, let me write down once again. Okay, I know energy operator form. Let me write down the eigenvalue equation. Quantum state is equal to energy operator of the quantum state. Okay, where I have IH cross dou by dou t psi of t. Okay, now this is a differential equation. Remember, I want to solve this. I want to solve this differential equation so that I would know how this is evolving in time. Okay, I want to know evolution. Okay, so for that I have to solve it or integrate it. Okay, so let me try to integrate. Fine. So now the question is, this is in a column vector. This is also in the column vector. This is in matrix. Okay, is it easy to do that? So there are some tricks or simplest ways. Okay, let's say the quantum state, the new quantum state. Okay, right? Yeah, I'm sorry. Yeah, so the new quantum state, which I would be getting, right? Okay, after I act, the unitary operator would be psi of t. Okay, psi of 0 acted upon psi of z would give me psi of t. This is what I want. I want to know that, right? Okay, so basically I'm trying to get what is unitary operator. Now straight away I can't do this. Okay, straight away I can't integrate it. So how should I do that? So for that there is a trick. Okay, what is the trick is, let me put as it is what are the descriptions of the quantum state I have in the column form itself, which is alpha t and beta t. Okay, so let me substitute back in this equation, and what I will have on the left side is, okay, a matrix. Remember, H matrix I defined earlier somewhere. Okay, just a minute. Here, H matrix I defined earlier. So let me use that as it is and put it here. Okay, so H acting on psi, right? So E0, 0, E1 acting on alpha t, beta of t is equal to, okay, and IH cross dou by dou t acting on alpha t and beta of t. Okay, see, we got that now. Now, just do the actual multiplication. You'll get E of 0 alpha t, E of 1 beta of t is equal to IH cross dou by dou t alpha of t, okay, IH cross dou by dou t beta of t. Fine. Now I have to, at the other side I have equations of two columns. I can simply equate each term. That is fine, right? Okay, let me equate that. So IH cross dou by dou t alpha of t is equal to exponential, sorry, E naught alpha of t. Okay. And similarly, IH cross dou by t, beta of t, if you want, one beta of t. Okay. Now I can just do the rearrangement in such a way, integration of, sorry, derivative of alpha t divided by alpha t is equal to minus I by h cross dou t multiplied by energy. I just put this one on here, okay, and send the alpha t to the left side. This is what I'll have. Now I'll integrate from some time to time, 0 to t, let's say initial to later time. Okay. So on the left hand side, I'll get a log alpha of t from 0 to some time t. On the right hand side, I have minus E naught h cross some t. Okay, complex I remember. Now send the, okay, let's put explicitly that the values of the limits. I'll get alpha of t0 by alpha of 0 is equal to minus I E naught by h cross into t. Okay, send the log to the right side. I'll get alpha of t is equal to alpha of 0 exponential minus I E naught h cut by t. So similarly, you can also get beta of t with the same integration, which gives me exponential my E naught h cut by t. Okay. For simplicity, I would write like this. Send, okay, write alpha of 0, beta of 0 on the right. Okay. So this is the like the time evolution of the probability amplitudes in time. You see, when you start with the probability amplitudes time independent, and we let the system to evolve with some energies. I'm sorry, this is one, and they evolve to this form. Okay, so I can write this now once again as alpha of t. I want to write in the form of column vectors. Okay, so which is exponential, sorry, exponential minus I E naught by h cut into t 0 minus IE1 h cut into t 0 multiplied by alpha 0 beta 0. You see now, this is a matrix. When acted on this, I'll get this right hand side. Okay, so the right hand side I have put in the form of one matrix product. Okay, so this I would say the quantum state, new quantum state in time is obtained by some matrix, okay, multiplied by quantum state at a very initial stage. Okay, now if you carefully see the matrix M, okay, which is its transpose is same as itself, and also it involves some complex terms, and it's equal to itself complex conjugate. So I would say M is equal to its M adjoint. Okay, right? Just a minute. Oh, sorry, I'm sorry. So transpose is equal to itself. Okay, it's not Hermitian, remember, right? It's transpose is itself, right? And one thing I observed is, if I just take its complex conjugate and transpose and multiply to itself, I would get identity. Why that is? Because, okay, whenever there is a transformation goes, a transformation of action of something onto something in a quantum state would preserve the inner product. Inner product means the length of the vector should be preserved. So the left hand side is a quantum state. If you just take an inner product of the quantum state with itself on the left hand side, must be equal to 1, and also the right hand side should also, inner product must be equal to 1. So the inner product of this with itself is 1, means quantum state with a break, M dagger, M, quantum state, must be equal to 1. So which is only possible when m dagger m is 1. So which means the m is unitary. It's giving unitary after multiplication. So whatever so whatever matrix you are mentioning here, transformation matrix is unitary matrix. Okay. So unitary matrix, let's say from now on will represent by U, which connects the system from 0 to t. So in general, they will write U of t, or even people write U t to t not t1, or t1 to t1 to, this way also they'll write, or this way also they'll write. They just interchangeably people write. Okay. Now I know how quantum states evolve in time. So why do I bring all these things? Because if I use a qubit for sensing something, okay, where did we have? So very early stage, okay. So we use a qubit for sensing. It evolves under some quantum surroundings, and how it evolves under that I am representing by unitary matrix. Okay. Let's say now we have established that. Okay. So unitary evolution is established. Fine. Now with that background, let me start the quantum sensing, the basics, the basic part of quantum sensing. Okay. Please remember whatever we discussed so far, but is going to be very, very handy. Okay. So now, what is quantum sensing, by the way? It is a method which involves a quantum systems. Okay. And these quantum systems would have some quantum properties. Okay. So the quantum systems used as a sensors undergo changes when exposed to external environment, which could be consisting of external fields. Fields could be magnetic fields or electric fields. Okay. Anything per se, right? Now these quantum systems are very, very precise, very fragile, by the way, very fragile, sensitive. So I can use them to sense the sensing, the fields. Okay. And how they sense the physical quantities. What are the physical quantities? These things. Right? Now, some of the historical examples of the quantum sensing is, okay, magnetometers. Examples. Magnetometers means they sense magnetic field. Okay. So what kind of a different magnetometers? There are basically three different magnetometers. One is superconducting quantum interference devices. Okay, we'll get to that exactly what they mean. Okay, another one is atomic based. It's called atomic vapors, means nicely separated atoms. Okay, or individual atoms also I can use atomic clocks. Okay, so they usually interchangeably used. Right? So quantum sensing rapidly going using these things. I say the branch of quantum science and technology is rapidly growing, right? So for that, the most common platforms being used, okay, is spin qubits. The platforms are the devices, you should say. Devices would consisting of spin qubits, like we just saw generic qubit, how it evolves, or it could have trapped ions. Okay. And also it can have something called flux qubits. Okay. It's a fancy name. Let me try. Spin qubits means if I just take a nucleus and electrons would be revolving around the nucleus. Okay. So there is an orbital angular momentum associated with the electron. Orbital angular momentum. So which is orbital spin. Okay, orbital spin. Not only that, electron revolves about itself. So that is a spin, its individual spin. And nucleus can also revolves by itself. So it will have a spin. So at a given point at a quantum regime, there is no fixed spin. It is always up spin or a down spin because of the dual nature, because of the quantum nature. At a given point, if I just try to observe the spin of an electron or a nucleus, it always is a superposition of up and down spin. So that is a qubit for me. So likewise, I can have spin qubits. And if I just take a trapped ions between the electromagnetic fields, the trapped ions could give me two quantum states in superposition. There is something called flux qubits, which is simply a micro level loops, superconducting loops, consisting of superconducting, which is actually the flux qubits. What is it is, the loops are created made up of superconducting material, and in between there are Josephson junctions were put. The cross symbols are Josephson junctions. Okay, so what I mean by Josephson junction is, so there is a superconductor, there is an insulator, there is a superconductor. It's a sandwich. Okay, material, superconductor, insulator, and superconductor. If I cool this system to millikelvin cooling. So here the superconductor would create Cooper pairs, which are seriously, okay, they are seriously active, and they even jump through the insulator. They do hop in between. So there is a current is constituted in this circuit. Okay, so this is actually represented as a cross symbol. So such superconductors are there in a superconducting loop. Now, if I just send a magnetic flux through this kind of a loop, it constitutes Josephson junction, right? It constitutes a current direction, either clockwise or even anti-clockwise. So basically at a given point, I would exist with a quantum state 0 and 1 corresponding to the direction of the current. Direction of the current in a loop. So I realize a qubit out of flux qubits. There's a flux current of magnetic flux. So magnetic flux would create a current. So current. Fine. So in that way, there are various different ways we can realize qubits. Now we need to exploit this. They are very, very sensitive, very fragile. So we can exploit their sensitivity. Okay. So quantum systems, they're sensitive to the external environment or external disturbances. So we can just check how they're sensitive. And basically, the idea of sensing is not just existing or coming up from the past few years. It is even explored before the birth of computers. Okay, sensing is being explored even before that. In 1931, by a person, a scientist by Weston, his name. So he used light meters, which are based on selenium photocells. Selenium photocells. Okay, based on that, the sensing is being explored. In a way, that is the motivation. So people started exploiting the sensitivity of the quantum systems for the external fields. Okay, so mainly we concentrate on the electric field and the magnetic field. So quantum sensing is for sensing electric field and magnetic fields. Okay, mainly. Fine, I'm sorry. Electric and magnetic fields, right? So how are we going to sense? We are going to sense how the quantum state evolving in time when it is exposed to them, right? So not only that, we can also sense the electric and magnetic field with respect to the frequency of the applied field, okay, and with respect to the temperature around this and around the quantum system, the pressure around the quantum system, and how rotations were induced with respect to different kinds of rotations also we could sense, okay, through that. Now there is a way to even get high resolution, high sensitivity, okay. Instead of using single atom or a single qubit, high sensitivity with the ensembles or entangled qubits. If you use entangled qubits, you could increase the sensitivity. Okay, how it is possible? We'll see. So interestingly, the change in one of the qubit would induce some change in the other qubit, entangled qubit. From there, we could explore. So this is a new technique being explored recently. Okay, fine. Now, what is it? The quantum sensing so fascinating. In a nutshell, let me give something. Okay, so it describes a method involving quantum objects like superconducting qubits or neutral atoms or trapped atomic qubits, which undergo some change when they get exposed to physical quantities like electric field and magnetic field. Okay, right? So the A part is physical quantity. Okay, physical quantity inducing change. Okay, right? And number two, right? So it uses something called coherence, quantum coherence, basically evolves out of superposition plus a superposition could be wave spatial or temporal or spatial superposition. Okay, so that could be used to sensing. Okay, and it describes recently the usage of quantum entanglement to improve the accuracy. Okay, and you can improve the sensitivity, okay, beyond classical limit. Okay, so this is the quantum sensing in nutshell. Okay, fine. So basically all the different forms of sensing would be covered under A and B. Okay, and if there is anything left which involves improving accuracy of, let's say, entanglement could be used. So that is the new domain, which is also covers most of the things. Okay, right? Fine. So now the next thing which I would like to give you is, okay, so we just said the quantum systems, how could we used to sensing, right? Now any quantum system could be used for sensing. Is the question is, anything, any qubit could be a sensor? Okay, that's the one question one should ask, right? Okay, just like the question being asked earlier, okay, is every quantum system would allow, okay, quantum computing. Okay, so answer to this question is, okay, so this is likewise, the answer to this question is given by a great person, DiVincenzo, by his own criteria. Okay, He gave it by some criteria. What is the criteria is the quantum system should have a discrete levels. Number one, it should be described by discrete levels. Okay, number one, discreteness. Okay, sorry. And if I just start a quantum system, so it should be allowing me to start with initial state or some classical form, zero ket. Okay, but the next thing is it should allow me to manipulate it, manipulation, so that I would create a superposition state out of initialization. Okay, and also quantum system should allow external intervention, external interaction. Okay, okay, right? So that is what the quantum system should allow me, right? And also it should be sensitive to the noise. Sorry, it should be rigid to the noise and sensitive to the signal. Okay, so I would say there is a change in the system in the form of some coupling parameter. Okay, let's say the quantum system energy separation is E. So it should undergo some change with respect to some external field with some factor of Q. What I mean is when Q is 1, it's a linear change. Q is equal to 2, quadratic change. Okay, so this is what usually the quantum division criteria would involve, so that if the system in general support all these things could be used to quantum computing. Similarly, the answer for any qubit is any qubit allow us to do the sensing. Yes, if the system satisfies division criteria like this, yes, in that case, we could say the quantum system could be used for the sensing. Okay, just whatever is the division criteria, we could also incorporate for the sensing systems. Okay, fine. Now that is being clarified. Now, can we classify? There are so many kinds of quantum systems around. Can we classify them? Okay, because it's easy to study each part, each kind by classification. Okay, of course there is a classification. So classification is done based on how the quantum systems would react, how they react, would react to external field. Okay, based on that classification is done. For example, one classification is charged systems. Okay, quantum sensing systems classification we are talking about. Charged system by nature, charged means they could be used to sense electric fields, electric field sense, because they're charged, by the way. And if you just take a spin-based systems, spin means magnetic field, we could use them to magnetic field sensing. See, this is how we can simply classify two types. Now, if you go a little bit more in the fact, a better sensor would be that would only respond to the physical quantity, not to the environment, not to the noise. But the thing is, it's not possible. So what do we want? We want more sensitivity to the external magnetic field or electric field, but less sensitivity to noise. It's difficult. So one has to make the balance. So the sensitivity in general, if I want to write, would directly proportional to 1 over the rate of change of the system nature with respect to external field, where remember V is external field. Okay, right? V means external field. V would take electric field or a magnetic field. Okay, so it should be inversely proportional to that, and there is something called decoherence time, T square root of decoherence time. So this is decoherence. So what I mean is, if I just take a qubit to exist in some superposition, Okay, it has to, electron should do the superposition continuously going back and forth, right? So superposition should exist for some time, but it will not, it will just decay because of the noise. Okay, because of the noise, it will decoher. That decoherence time is represented by this. So to have a better sensor, we should have very large, also very large coupling parameter or rate of change of the system nature with respect to external field. So this is what is prescribed for quantum sensor to be a very good one. Fine. So we just summarize for 2 minutes and then we'll give a 5 minutes break. Okay, and then we'll get back on the methodology. Okay, let me use my hand notes and get back. Okay, so okay, here I have my hand notes. Fine. So we started with what is a qubit, how it evolves in time, which is represented with some matrix, which is actually consisting some information of H. Okay, right? Information of H, right? So under that, how the system would evolve and system would evolve. So which comes out to be some operator U. So interestingly, that U operator is unitary by nature. So any transformation matrix is actually unitary by nature. So we'll just use that for future, right? So if the quantum system is evolving in time, which is represented by unitary operator, which would take some exponential of the Hamiltonian, the energy operator or energy matrix of the system. Okay, so along the process, we used the energy operator form as exponential, sorry, as a IH cross dou by dou t. So derivation I have given you here, and also there is a derivation for the operator for momentum, which I just said, IH cross minus IH cross by dou x for 1 dimension, for 3 dimension minus IH cross by the gradient. Okay, so that is also discussed for your reference. You can check that. Fine. Now, the quantum sensing, we just discussed what are the different kinds of sensings we can have, or we just defined what are the sensing is all about, right? So different sensors, semiconductor based or atomic or vapor, atomic vapor and atomic clocks. So we have to exploit the sensitivity of the quantum systems. In that way, we can detect the physical quantities like electric field and magnetic fields. Okay, I just gave what is a quantum systems in a nutshell. Okay, so that it covers all the existing different quantum sensing techniques. Okay, now the question is every quantum qubit could be a sensor, or every quantum system could be sensor? The answer is actually derived from Divisenjo criteria, which allows one to explain what are the possible quantum systems that allow quantum computations. From there, we just define the proper or a better quantum sensor. Okay, right? So there is a different class of quantum sensors just based on how they react to the external field. So two basic classes are charge systems and spin-based system. That is, I just discussed. Okay, and one has to strike a balance between the sensitivity to the external field, also the sensitivity to the noise. So that is what the sensitivity, the relation which I have given you here. So the exact expression we will see in the later part of the class or a session. Okay, so after giving 5 minutes break, we'll just get back to the quantum sensing methodology. Okay. Somebody having any doubts, you are free to ask meanwhile during this 5 minutes break. Coupling parameter, yes.
We'll take a 5-minute break, sir. Yeah.
Yes. I'll note down the coupling parameter.
Sure.
I'll just explain once everybody comes back.
Right.
Is quantum point contact an example of charge-based sensor? See, charged-based sensors are something like ions. Okay, so trapped ion-based systems could be a charge-based sensors. All right. So the how you bring them to the vicinity of the external field would be a question. Okay, so I hope that is what you mean. Is quantum point contact an example of charge-based sensor? Of course, yeah, because we are still talking in terms of single qubit sensors. In that way, you can say it's a point of contact based sensors. Yes. Yeah, I'll do that. So there's a question about hand notes. Kindly upload it to. Of course, I'll do that. My hand notes as well as my running note, both I will upload and I'll submit. Yeah. How do we manage for what duration electric field, magnetic field is applied? We'll come to that. Yeah, we'll study that. It's part of the methodology. Does sensing collapse the quantum system? Yeah, very good question. Yeah. See, something which is collapse means which is out of our control. Okay. So the way I bring my tool near the external field, I take the care. I take the care, right? So let me give an example in the real world. Okay. Suppose I have a furnace, gas furnace. The temperature goes beyond 1000 degrees Celsius. I would not go and use the tool, a regular thermometer, which hardly takes some 40 to 50 degrees Celsius. I will not go there with that. So I would use a high level thermometer there. Okay. So here question is, the external magnetic field is sensed in such a way, it would only induce the quantum state change. Okay. And it will not induce the collapse of the quantum state. Okay. So that care I would seek. How do I take? I would ensure the way I prepare my tool, just like the thermometer, which I gave an example. And there is a way to even devise and tune the thermometer in the quantum case. Okay. So that is, we will all discuss. Now, the one which is, there is a possibility to collapse also. What is that collapsing? The quantum state is collapsing because of what? The external noise. Okay. Which I have no control. So at the most, what I can do, I can just secure the system away from that noisy factors. I can try my best, but it's impossible in quantum systems since they're so fragile. So the noise can induce a collapse. Okay. So the care need to be taken, how the collapse could be addressed, those things need to be taken. Okay. So I would say that is the answer for your question. Does sensing collapse the quantum state? Yes. So I would choose the sensors in such a way this collapse would not happen and the systematic evolution would happen. Based on the evolution, we will study the quantum sensing, or we'll get the nature of the external field or external quantity. We'll discuss all those things. Where will sensing in quantum scale be useful in the macroscopic practical world? Practical world. Okay. Yeah, see, practical world, the immediate applications is medicine. Okay, one is medicine. that is like, for example, currently MRI, CT scans are all there. Na? If you could replace those things with quantum sensing, it is predicted to be like few orders of more accurate than the existing technology. So this, it's emerging field. The people are working, and lots of research is going on. For drugs, probably, but immediate application would be medical diagnostics. So that is the main application in the real world, in the macroscopic world. Actually, it's like from microscopic, you pile up all the information, you make it macroscopic, just like computer-based tomography, CT scan. The same way you can realize the atomic level resolution of the human tissue. So it's like you can realize, or you can diagnose the cancer at even much earlier stages than the existing technology, diagnostics technology. Okay, what is the difference between measuring and sensing? Okay, sensing is a very broad section. So measuring is existing inside that. Okay, it's like a sensing is a bigger Venn diagram. In that, measuring is a part of it. Okay. So will the sensor get entangled with the measured system? Okay. So this is how people like, yeah. So it's a very interesting question, because quantum computing means superposition and entanglement. Entanglement being thrown everywhere. So the question could be even asked, when you trying to do the sensing, will the sensor going to entangle with external field or external environment? So it's all depends. So I would not say yes unless you are deliberately doing it. Okay, right? Yeah. Will the sensor get entangled? Yeah, that's the answer I just answered. Unless you are trying to entangle, it will not be possible. Can measurements in quantum circuit design be replaced by quantum sensor? So there are less chances of collapse of state. Yeah. See, sensing means you carefully does the measurement, bringing things very sensibly. Okay. And you can't replace the measurement with a sensor. Okay. So there are places you need to measure, and you need to convert the quantumness to classicalness using measurement gates, right? So yeah, so there is something called readout ions people use, for example, in quantum memories, sending information into the system and retaining the information in the form of qubits. Later read out the information of the qubits without disturbing the qubits and their nature, without measurement. So that is being explored back then when I was working in Sweden in one of the experimental group. They were using atomic combs to realize qubit memories, and there they use the readout ions. So in a way, you could say the readout ions are the sensors which gets the information out of the qubits without disturbing the nature of the qubits. So that the qubit readout ions are the readout atoms or readout qubits are designed in such a way. They are like special players, I would say. Okay, I think we'll start. Dr. Pillai, can we start? We stopped at 3:06. I think it's more than 10 minutes. What is a quantum machine and quantum sensor? A machine is a bigger picture, and sensor is a part of it. Okay, a machine which allows us to do computing. Okay, sensor is just allows us to just sense something. That's all. Okay, right? Okay, fine. I think we can start. Yes, so more than 10 minutes passed. So let me get back to my hand notes. I'll change the view. Okay, right. So yeah, we have close to 1 hour time, right? So here you can see the quantum sensing methodology. Okay, that's what I want to discuss now. Fine. Now, let me use, instead of just reading through the content, let me explain. So with the board, that would be easier and better. It'll have more effect. Okay, the methodology. Okay, the QS stands for quantum sensing methodology, right? Probably you might be having some idea by now. It involves three basic steps. Number one, initializing this sensor, initialization. Okay, initialization of quantum sensor. Let's say we initialize to a classical bit state. I'm starting an atom in the ground state. Okay, when I say atom in the ground state means the electron possibly in the ground state. Okay, when I take an atom, it can have energy because of the electron jumps here and there from their surrounding temperature. If I cool it to millikelvin, okay, cool, then I'll have electron in the ground state. That is why you see a large cooling cylinders in the quantum setups, in the experimental labs. Number two, what I need is I want to allow the quantum system to interact. Our system should allow to interact with the signal. Signal in the sense external field which I'm of interest. Signal which is of interest. Okay. And so it undergoes some change, evolves into some quantum form, evolve when it interacts. And the next thing, what is my basic methodology step is reading out or analyze the quantum state to make out or to get signal as such, signal details. Okay, this is the three steps involved in the methodology. Okay, so how the evolution would imply the signal details? Probably through it acquires, through acquiring, okay, some quantum phase. It acquires some phase, right? Okay, and it may undergo some change, which is not the phase or something else. So just by finding how much change it undergoes, based on that, I'll make out what is my signal is as such. Okay, right? So I can improve the precision beyond classical limit if I use quantum systems that I said earlier. Okay, right? So people use the photonic based, okay, photonic based sensors involves quantum interference, right? You guys, interference means you might be recollecting Young's double slit experiment. If there is a light source comes, there is a two slits, the light goes through the slits and these two also acts like a source, S1, S2, and this is a source, yes, and the light from here would reach to the screen with some phase, and this would go and reach to some phase, and both are in phase. There is a constructive interference, bright. If they go out, they reach out of phase, because let's say at this point the ray goes, hits like this, this one ray goes and hits in the opposite phase, so this would be destructive interference, so dark fringe. Okay, so constructive and destructive. Okay, so two light sources creating interference, bright fringe, dark fringe, bright, dark. Okay, bright, dark. So in that way, the interference is created. Interference. Right? Similarly, I can use two fields, pump and probe, in the sensing mechanism. And this is, I want to induce and put the quantum sensor under this, and that sensor would become so sensitive in presence of them to the external fields. Okay, so that is example in the case of NV center in the diamond. Okay, so where diamond, okay, I hope my drawing, so the NV center is like a dipole, right? You put a pump and probe field. Okay, so there are electronic levels associated with this NV center. So those level get split because of external magnetic field. So because of split in the electronic orbits, so the pump and probe field will only interact with these split lines under certain scenarios. If the magnetic field is or electric field is such a level, only in particular level. Okay, if there's a green light is put on this, a pump or green, we would get a pink or some other different color. If no light is coming, in that case the sensing is not done. So depending on the color coming out, I would sense the magnetic field. All right, so this is what the sensing is based. Usually it's called interference based spectroscopy. Okay, so there is a series of measurements are also performed here to reconstruct. Okay, series of measurements needed for reconstructing the external fields like electric field and magnetic field. With just one reading you would not get, because quantum computing is all about series of experiments. It's like a tossing of a coin. Okay, now this is the gist of quantum sensing. Now let's try to put that into some mathematical form so that we will understand better. Okay, so far we were talking in terms of the quantum system being exposed to the environment. Let's say environment is not there, I'll have system Hamiltonian as it is H naught. Okay, where H naught, I just gave an example, which is having E0, E1. Right? Now I'm exposing that to the external environment. So there is a field Hamiltonian is also coming to picture. Let me say this is time dependent. Right? Now, as somebody was asking, how are you going to ensure the system would not collapse? Instead of it just keeps under control. So for that, I'll have a Hamiltonian. It's called control Hamiltonian. Okay, it's like a tuning thing which would control, allow me to control. So system is going out of my view. I want to put back into my view. In that case, I would use H control. So the overall Hamiltonian would be this. Okay. Somebody was asked earlier, what is a coupling factor? We'll explain what is the coupling factor along the way. Right? Okay, fine. Now this is a Hamiltonian would be. Now the just a system Hamiltonian, a qubit Hamiltonian would be represented like this. Okay, basically it's a just two level atom. I always, anybody in quantum computing always draws a qubit picture like this. Okay, here the energy separation is H omega, okay, or H omega naught, which is equal to E1 minus E0. Fine. Now there are three terms involved. This is systems without any environment. This is external field or interaction Hamiltonian. This is control Hamiltonian. Okay. Remember, this is static, no time dependency. That means system would emerge under this in stochastic manner. Okay, right? It's like without any environment. The moment I bring in the other two terms, that I'm talking about the environment. So you can say together it's called a quantum bath or surround. Right? So now the question is, the interaction would induce, so if I just take a qubit, okay, interaction could be because of the presence of other two parts of the Hamiltonian, the energy levels could just displace, so that the energy separation would go anything other than the existing value. Okay, that is one effect. The other effect is, say if the electrons are hopping between 0 and 1, like a superposition state is existing, it's called Rabi oscillations. If that superposition is there, the superposition itself will decay because of the noise, or because of the external field. If the electrons were forced to decay back to the ground state with some decay factor gamma, so that also may happen because of external intervention. Okay, remember that. So this may be the effects, external effects. One is this stretch or even compress, so that energy separation would change. The other one is forced decay of the electron from excited state. Okay, fine. Now, so that is the external field effects, right? So can we put that into some mathematical form? So let me put HV of T into mathematical form, which describes this effect of either stretching or compressing the external field, energy separation, or induced forced decay. Okay, so that is people put in the form of Hamiltonian part, which is exist in parallel to the qubit description or a qubit alignment. The other one is for a field applied perpendicular to the qubit description or qubit alignment. Okay, right? So the one is V is parallel, the other one is V is perpendicular. If the qubit is there, electric field arrangement is in parallel with the qubit arrangement or superposition. In that case, I would capture here. If it is applied field is perpendicular to the qubit, okay, qubit description or qubit alignment, I would have V perpendicular. Okay, so this component, what I say here is in general commutes with the overall Hamiltonian. Commutes means H into HV double multiplication, is equal to V HV into H. So this is a commuting effect, or you people say commutator, H comma HV double dagger. So V parallel is equal to 0. It's a commutator. Commutator is 0. Basically, this is what. Now, what is its form in general? Would look like is equal to half omega, gamma, some factor of field multiplied onto one outer product with one ket minus, okay, 0, right? Okay, so you can say 0 0 or 1 1, doesn't matter, more or less both are same. Okay, so this is the Hamiltonian, which is commutes with the overall Hamiltonian, the interaction part, right? The one which is not commuting is, okay, for simplicity, let's put a 0 here, a 1 there, okay, to avoid the confusion. Right? Now, what is the perpendicular component of Hamiltonian? That would be again half into gamma, where gamma is, I'll come to that, it's a coupling factor Okay, V perpendicular, right? It will go inside V perpendicular of T 1 0 plus V perpendicular adjoint 0 1. I'll tell you what it is. Okay. Now the gamma which I have here, the coupling factor is nothing but, let's say the energy separation is E between the levels. Okay. When I expose the system to the external field, that energy separation undergo change with respect to applied external field. V is not a voltage or something, it is a field strength. So this is energy separation, energy, this is applied field. Okay, and gamma could be a first order derivative or it could be second order derivative. Okay, so I was earlier I was giving the coupling factor is equal to a rate of change of V with some orders of applied voltage strength. Okay, so this is a coupling factor. Basically it tells me how much change is induced because of the external field, and it's also called transduction parameter also. So easiest way is coupling factor parameter. Okay, fine. So I hope I answered the question which is raised earlier. Now if I had to write the Hamiltonian in the matrix form, that is the idea, right? You see, this is a matrix 1 0 0. Okay, and this is a matrix 0 0 1. Okay, and this is a matrix 0 0 1 0, and this is a matrix 0 1 0. Okay, so basically what I get, the interaction Hamiltonian would be, overall interaction Hamiltonian would look like gamma by 2 V parallel of T, V perpendicular, please cross check if somebody is carefully watching it. Okay, this is an interaction Hamiltonian. Earlier I had a system Hamiltonian. Okay, the Hamiltonian of this H naught and HV of T I just wrote mathematical form. So what is the explicit form of V? Probably we don't know. We just apply from some source and we will find out what is this V, the strength of V from the sensing technique. Okay, so one simple example is, like I said, if I just take orbits 0 and 1, because of external magnetic field, what happens? The ground state splits into two more. External excited also split into two more. I just giving one simple example. Okay, when external magnetic field is applied, the orbit splitting is called a Zeeman effect or Zeeman shift. Okay, right? Magnetic field inducing, and even electric field also induces such shifting of levels and splitting of levels, which is actually due to called it's a Stark effect or Stark shift. Okay, so you see the energy separation is undergoing change from initial form to some other form not equal when external field is involved. So the presence of the change would be due to these things. By knowing the change, manifestation of electric and magnetic field is done. Okay, right? So now let's try to get into little bit more details. Okay, right? So I'll just give one more mathematical description of this the vector V of T, right? The external field. Okay, external field. Okay, let me write, say V of t. So V of t is representing electric field, magnetic field. Magnetic field and electric field are usually vectors. That means this would have a component along x direction, y direction, and z direction. Just like any vectorial field, so V could be three-dimensional vector. Okay, so that means if external field is represented in a vector form, so in that case, the Hamiltonian would be a gamma vector V, a dot product with the Pauli matrix sigma. Okay, this is a vectorial representation of the energy, interaction energy system. Okay, so specifically what is this? It will have X Pauli matrix, Y Pauli matrix, Z Pauli matrix. Okay, right? Hat for even unit vectors is there, hat for sigmas also there. So basically what I get here is Vx sigma x, Vy sigma y, Vz sigma z. Okay, sigma x and sigma y and basically x gate, y gate or y matrix or a z matrix or a z gate, right? So so why you are bringing in terms of vector, and here you gave in terms of parallel and vertical perpendicular component, right? So of course there is a connection to even for this. The Vz which I have here, the Z component, which is simply the parallel component of V of t. So the Z component of external magnetic field would induce, okay, the change in the change in the system energy separation. Okay, and what about the perpendicular components? So the perpendicular component is actually equal to Vx Vy in the complex form. So this is a perpendicular component. So basically the real part of V perpendicular is Vx, okay, into sigma x plus imaginary part of V perpendicular into sigma y plus V parallel into sigma z. Okay, all are time dependent, remember, I should not forget that. Okay, would give me the interaction Hamiltonian. Okay, this is a mathematics, so no need to remember. So this is a, since it is a basics, this is how I'll just incorporate or bring in external field interaction with the surroundings, interaction of the surroundings with a quantum system. Now I've just described, okay, I just went back. H involves the system Hamiltonian, external field or interaction Hamiltonian, or there is a control system, control Hamiltonian. Let's come back and let's see what is that control Hamiltonian is. Okay, H control, which is, by the way, it's also time dependent. Okay, so what it can be explicitly, it could be some gates, some basic gates. Okay, why do I need them? Using them, I would control and tune the system to as per my requirement, as per requirement. Okay, in that way I would do that. Basically it involves some basic gates. Okay, so there is a way, let's say I would use Hadamard gate, right? So I'm sorry, Hadamard gate. Okay, so my pen is Hadamard gate, right? That is a H gate. So don't confuse with this Hamiltonian H, the Hadamard gate H. Okay, or I could use Pauli X, I could use Pauli Y, I could use Pauli Z. Okay, so I could use some rotation gate about angle 5, Rx gate. about x-axis rotation, ry gate about y-axis rotation, okay, and rz gate about pi by 2, right? So some of them directly give these vectors, so these matrices. So basically I use a basic gates and I will try to control the system, a single system, let's say single qubits, a sensing qubits, by the way, sensing single qubits are controlled or tuned by these gates. Fine. So now accordingly I can define what is my gates. Now I define my Hamiltonian also. The question is, I am just giving you a gates. What is the corresponding Hamiltonian? There is an easy way to get that. Let me tell you how to get that, or how to explain what is H control would look like. Earlier I gave you a Hamiltonian which was looking like this, you see, and under this Hamiltonian, system would undergo some evolution, so which is equal to having unitary action, unitary matrix action of minus I H T by H cross. Okay, so that is a unitary matrix. Now suppose there is some matrix Hamiltonian A which I don't know what is consisting of, okay, right? The corresponding unitary operator for that unitary matrix is exponential minus IA T by H cross, which is equal to some gate matrix operation, for example Hadamard gate, okay, so which is 1 by square root of 2 1 1 1 minus 1, okay, right? So knowing the gate operation which is equivalent to unitary matrix, I can get back what is my A is, okay. So where A is a Hamiltonian, control Hamiltonian, remember, okay. So the control Hamiltonian would induce a gate operations like this. Knowing the gate operations, knowing gates, I can get back control Hamiltonian, okay. You can do either way around. You knowing the control, you can know the gates. So basically how to control the system you would know, and you can describe the Hamiltonian, or knowing the Hamiltonian, control Hamiltonian, you can get what kind of gates I should use in the sensing process. So with this I have described what is the Hamiltonian consisting of. It will have the system Hamiltonian, the interaction Hamiltonian, and the control Hamiltonian, okay, right? Last two are time dependent. The first one is static, it is cannot be time dependent. Since I know H, the overall H, I would easily find out what is the unitary matrix which would induce change in the system, okay, right? So which pushes the quantum state from initial form to new form, okay, right? Knowing that new form, knowing, I can make out what is HV of t, okay, and further I can make out what is V of t, okay, make out or figure out further, okay. Now since I'm only talking about single atoms, suppose let's say involve couple of atoms for sensing, okay. So there, if I involve, in that case I would be not just needing only single qubit gates what I gave you earlier here, okay. So single qubit gates, these are all single. I would be needing multiple qubit gates. The first multiple qubit gate which comes to your head, okay, is C0 gate, okay, which is this, or any controlled unitary gate, or some controlled phase gates, some phase gate, right? So remember Z gate is actually phase gate. Why? Because Z matrix is 0, 0, sorry, 0, 1, 1, 0, and this one, which is exponential I pi. You see, this is inducing a phase change of relative phase of pi to the quantum superposition state. Okay, so this becomes negative when I act Z gate, Z acts. Okay, so just to give a glimpse how multiple systems are involved in that case, how the control is done, control requirements. Okay, all right. So don't worry, if my handwriting here is not understood, you can read through the notes. Okay, now fine. So methodology, under the methodology we defined the quantum system initialization and the system description. Now knowing the system description or the Hamilton description, I'll evolve the system, and knowing the evaluation, I'll make out the system, what is it consist of, it is undergoing through the interaction wise. Okay, now the next thing is, can we put that into some steps, some kind of a protocol, some kind of algorithm, so that I can just give a set of steps to somebody. Okay, so let me get back that quantum sensing protocol. Okay, just for a revision, as you guys know. Okay, let me see, is it allowing me to go to the next page? Yeah, I am exhausted. Okay, so let me take one more sheet. This is record saved. Let me save that. Okay, export as image. Hope it is exported. Yeah, it is exported. Let me get back to the new sheet. Okay, 1 minute. Okay, the new sheet. Now the quantum sensing protocol. I want to give set of steps so that somebody can follow through. Okay, right? As you guys know, the quantum sensing methodology involves 3 steps. Number 1 is initialization, just a recollection. Number 2 is interaction with the environment or external field. Number 3 is reading out or making information out from the evolved state. So these are the 3 steps involved, right? So basically my protocol would involve those 3 steps, right? So let me put in that form. Number 1 is initialization of the quantum system. Let's say I'll just initialize the quantum system, quantum state initialization to 0 basis state. Okay, because the system can exist in 0 or 1 at a given point. So I'll choose system is in the ground state. This is a basis in which I define my system to be initialized. Okay, now I want to, okay, I want to induce the change in this ground state to become superposition state, because the ground state is a classical form. I don't want the classical form. I want to have a quantum form, so that the quantum forms are very, very sensitive to the surroundings. So I want to induce such change. So what I do, I want a superposition. So I will induce a change onto ground state, initialized state, to become superposition. Superposition evolution. Okay, which is look like superposition state like this. Okay, how did I do? Let me say there is a unitary operator, initial unitary operator, which I use which puts the quantum ground state or a single bit state to superposition state. Okay, this could be, remember, a superposition state. I'm just giving one example so that you would know what I mean. Okay, right? So how do I do? A simple example would be, take a zero state. Okay, take atom in the ground, right? Send a pulse pi by 2 pulse. It's called pi by 2 area pulse. If you send, there's a bunch of photons would go, put this electron in the superposition of ground and excited, which becomes like this. Okay, so in the form of quantum computing, what I'm doing, I'm just sending a quantum state 0 bit through Hadamard gate, which becomes a plus state, superposition state, equally superposible. If I want unequal subgeneric, I would have a specific Hamiltonian for that. Okay, right? This is a special case of above. Okay, right. Now the second step of the protocol we know, right? Now the third step is interaction with the, let's say, field V of t, right? So R with interaction or evolution in presence of the addition component of interaction Hamiltonian. Okay, remember, when I say only this is, when this is there, it doesn't mean only this is there. It is a part of this is existing. Okay, sorry, existing along with the system Hamiltonian. Okay, along with the control, all are there. In addition to that, this is there. So that is what the interaction part. Okay, right? So because of this interaction, presence of this, okay, the system would undergo an evolution with some unitary matrix, which is described by overall Hamiltonian. Remember, overall Hamiltonian. So which systems pushes the system from 0 to t. Okay, so u size 0 to some new level t. Okay. Okay, so for your simplicity, if you want to put in a bracket, you can put. So that's a system like a Hamiltonian gives the unitary description. Under the unitary description, quantum state psi of 0 goes change and becomes like this. You see? So that is a step 3. Fine. Now, remember, psi of t could be a combination of the old state or a new state. Okay, so let me say now a old state and new state psi 1. Why I'm saying, because since it is in quantum in nature, I can never be certain. When I say psi of 0 goes to some new form, means not the entire psi of 0 would become psi of 1. Okay, so it could be a combination of both C0, C1. Remember, so where C1 and C2 are complex. Okay, just as idea. What is, I will never succeed in creating 100% of psi of 1 from psi of 0. It is always combination. Okay, right? Now I have psi of t coming from, sorry, step 3. Next, I want to read that out. I want to analyze that. Remember, psi of t is in some form, some superposition form, okay, which I don't know. So I want to put that into my readable form. What is that is, the basis states I am starting here is 0 ket and 1 ket. Okay, this is some basis state which I don't know. Okay, without disturbing the quantumness, I can project this onto the basis which I know. The basis which I know is 0 ket and 1 ket. Into that ket I can project. So what I mean by projection is, again, come back to the classical, the classical analogy. For example, I have a pole here, current pole, right? If you just put a light from here, okay, so this light would cast a shadow of this length. Okay, so this is a pole, current pole is projected onto ground with some shadow. So it's a light is actually projecting. So by knowing what is the shadow, all right, okay, and also knowing the theta here, I can easily make out what is the length. So that is a trigonometry for you. Now projection is nothing but casting the length of the system or the image of the system into some other dimension. So here, this is the some basis on psi of t is described or coming up with some basis which I don't know. Let's say I want to project onto the basis which I know, right? So how do I know that is I would bring in some another matrix unitary operator which would put the quantum state, evolved quantum state, into my quantum state alpha, where alpha is defined in terms of basis state 0 ket and 1 ket. Okay, remember earlier, starting from 0, okay, it becomes superposition in 0 and 1s using unitary operator u of a. Now I am ending up with some other basis. I want to go back to the same basis which I defined earlier. So I would have the unitary operator B. You can see interestingly, whatever effect unitary operator A is creating, putting systems from some other form to the basis of 0 ket and 1 ket, okay, and some other form to the basis and 1 ket, the unitary operator B also causing. So basically you can say they are of reversal, one of the reversal of the other. It's like one dagger or joint of U of A is U of B. This is just for your information. It may not be guaranteed, not guaranteed every time. Okay, right? So now we will exactly get what I mean when we choose one example. Okay, so let me go to the fifth step. What is that fifth step is? Now alpha is defined in 0 ket and 1 ket. Okay, so simply what I want to know how much contribution comes from 0 ket, how much contribution comes from 1 ket. Okay, this is alphas are actually coherent states. Coherent state. It is just like psi alpha 0. Don't confuse with this alpha and this alpha, remember. Okay, like this. Or you can just say, let me write A and B here, A, B. Okay, right? Now, the component of A, probability amplitude, component of B, probability amplitude, would give me what is the probability of when I make a measurement on psi, what is the probability of getting 0. Okay, let me say, if M is measured, give me probability of A square, probability A square, which is equal to A square, with 0. Or you can say, when I make a measurement on psi, gives me 0 with A square. When I make a measurement on psi, and I'll get 1 with beta square, sorry, B square. Okay. Now a quantum state is given. How do I know I'll get 0 when I make a measurement? With what probability I will get? What I'll do, I'll simply take an inner product of 0 with psi. You see, interestingly, inner product of 0 with A0 plus B1 gives what? Inner product of this 0 with 0 is 1. Inner product of 0 with 1 is 0. So I'll get A. Okay, the amplitude I'll get. If I want to get a probability, I'll just square it. Okay. Similarly, if I want to get what is the chances of getting 1, I'll just take inner product with 1. which is beta square or b square. Fine. So to know what is A and beta, answer A and B, I have to perform the measurement on the coherent state, right? By performing coherent state, I would get A square and B square. So which is like probability 1 and probability 2, or probability getting 0, probability getting 1. Remember, this is only one experiment. Okay. But with one experiment, am I able to get V of t? No. So I have to perform several experiments. Let's say n times. In that, I'll get a distribution of P of i's, okay, 0 and P of I 1. Okay, where I runs from 0 to E times. Okay, so for a given, so what I'll be getting Px. So if you just sum the probabilities, it should give 1, right? Now you would be having a set of probabilities where k runs from 1 to n. Okay, so from the set of probabilities from obtained, I would from that I would get, okay, I'm sorry, something happened with my pen. Okay, okay, so I think it's not allowing me, I don't know, something strange. Okay, it got exhausted or something, battery or something. Anyway, so let me get back to my notes now. Okay, and summarize. We are over time. Okay, fine. So where are we? Yeah, here. So we'll make out of A square and B square, and I will do the same thing for the ensemble. Means n times I can do, or I can do n such setups and do that. Basically, I am talking about one qubit used as a sensor, perform the same experiment several times, or I can take like same kind of n qubits and perform the experiment once, and then take the probability distribution. From the probability distribution, I can make out what is the, see, p of case here I have, okay, the p of case which I mentioned here, okay, just a minute, p of case. So this is p of k. So using P of k, I can make out what is V of t. So just to give a summary of what is the algorithm or the protocol would look like: initialization into bit state, creating superposition state, evolve the superposition state under external field, and then put the superposition, like evolved field, into measurable coherent state and measure the coherent state. Okay, and let's say I want to measure what is the chances of getting 1. In that case, 1 minus inner product of 0 and alpha absolute square would give me the probability of getting 1. So I perform the same things like several times. I perform the same experiment, same kind of experiments once for n samples. I'll get V of t. Okay, so I'll conclude here. Tomorrow we will see the specific examples where sensing could be done. So with that, you would understand what I mean, what is this protocol is all about. The exact examples we'll see. With that examples, you will exactly know what I mean by this quantum sensing. Okay, right? So I'll stop here because it would be too much mathematics. Okay, so in tomorrow's class, we'll see those two examples we'll see, and then we'll get back to this what is the second part. Okay, what I promised. Okay, just a minute. the second part, that is single photon and entangled photon evolution, the basics. Okay. Okay, the batteries are getting. Okay, fine. If there is any doubts, please ask me now. Let me see the doubts here. Okay. Some references for today's topics, of course, yeah. So the references which I used for my talk today, it's a combination of one review article, okay, right? And the books called Nielsen and Chuang, Quantum Computing and Information Theory, right? And there is a book called Quantum Mechanics by Jet Li. So that is the book. So 3 references I have referred, and the most of the part is recent review based on recent review article. Okay, so let me quickly show that review article for you. All right. Okay. I hope. Anyway, I'll share the review article with the team, academy team, and they will share with
Yes,
you.
you can share it with me. I will post it to all of them. Yeah.
Yeah,
We will
yeah.
include it in the material that is there along with the slides. You will be giving us a PDF, sir, now of this course.
Yeah,
Of
yeah.
this,
So this is
material.
what are you seeing right now is my
Yes, sir.
hand notes. Okay.
Yes. Yes, sir.
So this is one, and this is the other one, right? So
Hmm.
I hope the system getting hanged. It's charged anyway.
Yeah, आप आराम से कर लीजिए. Maybe you can do it a little later. No problem. You can send it.
And this notes also I will give. What you are
Right.
seeing, this is a hand notes, which
Right.
consisting of everything in detail. Okay.
Okay.
Whatever I said.
You told me that you will give a already pre-prepared this is pre-prepared
Yes,
notes.
yes.
Then you have the lecture notes, right? Two sets you will give, right?
Two things
Sure.
I have. Okay, so the plan is to make this is 30 plus pages and notes into the typed version. If somebody is not able to understand my handwriting, for them I would try, because there's a lot of mathematics. Let's say here mathematics, so it's not that
Right.
easy to prepare slides for that. But anyway, that is the ultimate the target, because ACTE may be needing that. So
Right.
yeah, we'll do that.
Yeah,
Okay.
maybe by Sunday, if you can give it, we will conclude the course. We will give the what do you say, the course material. We will add these and we'll give.
The
You will have
typed
time.
version, sir? Will I say?
Yeah, maybe later also we can give, no problem.
Yeah.
That's not an issue.
My PDF version, the notes which I use for teaching, that is all I will give. Okay.
Right.
So the typed version with the equations would slightly, I need more time, because
Yeah. You will have to do a LaTeX version.
yeah, the content is seriously too big.
Right.
Yeah. So let me see some
Sure.
questions here. Outline about tomorrow's examples. Okay. So tomorrow's examples, we will be discussing the protocol which I described today. Specifically, for example, how I am going to detect the external magnetic field which is near the quantum sensor, or electric field near the sensor, how it is inducing some changes in the sensor. So 2 examples we'll discuss tomorrow. Okay, quantum sensing basic notes or references or videos are required. I would feel, I did check if there is anything available on the net or anywhere video. I didn't see anything. Even the textbooks also not that straightforward. So I made myself, as per my knowledge goes, this is the simplest, I took a simplest way to explain things. So if you go through my notes, I would say you would get the actual, just the basics of quantum sensors. You would get that, the mathematical description, how that allow you to sense something, you would get. So yeah, I would what I should say, I would credit this to a review article which I would be sharing. Okay, let me okay, this is a review article. This is a quantum sensing by CL Dagan and F. Reinhardt, and P. Capillaro. Okay, so P. Capillaro is a supervisor of Professor Kavita Saha, sorry, from IIT Mumbai. Sorry, Kasturi Saha. And yeah, this is a review of modern physics 89035002 publication. Okay, so this publication I would share, don't worry. Right. Yeah, any other things I can see here? We will be reading either magnetic field or electric field in iteration, not both at right? You can do both at a time. That is also possible. Okay. So for understanding point of view, we started with just one field. If you define your Hamiltonian consisting of both the fields, of course you can read the effect of both, and from the effect you can make out what is this electric field and magnetic field, the description as such. Okay, can you give some hints about what you will discuss tomorrow? Like I said already, can you please email of yesterday's speaker? Okay, I think the Pillai sir will give Venkat sir's email ID. Can you apply QC effectively to earthquake sensing accurately? Yeah, it's a very interesting question here. Right. Of course, yes, earthquake sensing. It's all about the trembling, the vibrations. Okay. You can come up with some sensor. Yeah, it's a one field you could start working towards. It's an interesting field. Okay. Anything which can induce some change in a quantum system could be a means which we can detect. Okay, so as of now, that as per my knowledge goes, that field is not started. I think you can initiate. I think use some sample of basic programs which I can run an IBM Pro Quantum as practice of 10 minutes. Okay, yeah, you can start with the let's say the phase estimation algorithm, or there's something called Bernstein's Vajrani algorithm. Okay, that is the simplest algorithm, right? Or a Dutch algorithm, Dutch-Joyce algorithm. These are very basic algorithms. You can, if you know them, then you can start working on them. Okay. Can we have those books on the canvas? Yeah. The books, yeah, those and the book, Nielsen Chuang, I will share. Could be one of the option where draft accuracy seismic models could be improved by introducing quantum algorithms. Yeah, again, somebody was asking about earthquakes. No? Yeah, adding quantum computing, we could improve the accuracy of seismic models. Yeah, that is possible, right? So that's the one field. Yeah, even I did my PhD in nonlinear dynamics in combination with quantum optics. So that's a one field we could definitely explore. Yeah.
Yeah, regarding the books on this thing, ebooks, we will try to share it through WhatsApp because piracy issues will be there if we do it on what is called on Canvas. Canvas always asks whether do you have the permission to share, right? So slides, because we get the permission from the speakers, we are able to share. Books, maybe I'll see if sir can share to me. I will put it in the group, and then actually it is you understand, right, what we are doing. So.
Correct. Yeah. So, this we don't know. See, this Nielsen and Chuang book is available throughout the net. Just search Nielsen and Chuang quantum information theory and
Nielsen will
computing.
be available, so you can any one of you can get it directly from the Google.
Correct. And we don't know whether we are allowed to circulate officially.
Correct.
That is the tricky thing. So this review of modern physics, like review of modern physics paper, which I said, which is also available on the net, I'm allowed to share because this is one of the best review articles. So they put it for open publication. Okay, so yeah.
Yeah, that document we will upload, sir. Wherever they have given rights, we will upload that. Yes, thank you.
And for hands-on on IBM, probably there is a separate course for that. Please
QT03, QT0304 combined, we are trying to do it. So that will come.
Yeah, please don't hurry.
Because,
don't hurry. Be patient and slowly you try to accumulate one by one. Don't try to do everything at once. So you might got some idea about gates, how gates act, And same thing you can graphically see with a graphical interface and IBM quantum experience. Okay, so that will also be introduced soon in the next course. That time you would be able to do like what Venkat sir was referring yesterday is how to start using IBM experience, quantum experience. That is what he initiated. Okay, and if you really want, you are very curious, you can't wait till the next QT02 or QT03. There are tutorials definitely available on the YouTube, and you just search how to use, how to explore quantum IBM experience. There is a simple tutorial videos are there. You can just follow that. Okay, so can you suggest book for quantum cryptography as well? Okay. Yeah, I think to be starting with Nielsen and Chuang has the fundamentals of cryptography also. I would say that is the first point of initiation. So I would recommend that book. That is like in a way Bible of quantum computing, consisting of everything. Even quantum physics is also there. Linear algebra is also there. Introduction part which is required for quantum computing. Everything is there. Okay. Oh yeah, somebody shared a earthquake model. Okay, there is a paper. Okay. I think you, I hope you have my email ID. So please do share. I'm sharing my email ID. Okay. We can have further discussion on that. Okay. If quantum computing is used for that particular earthquake model, we can explore. Yeah. Please name once again quantum cryptography. Okay. Book. Okay. Okay. Let me. Nielsen and Chuang. Nielsen and Chuang. Okay, this is a book. The authors, the names of the yeah. Right. I hope I made some sense out of today's 2-hour session. Okay, I'm sorry if I had made some mistakes while describing few things. You can get in touch with me and let me know if there is any suggestions for my class today. I would say class because I did most of the Blackboard. Okay. Yeah, Nielsen and Chuang itself is for okay, post-quantum cryptography. Oh my God. Okay, post-quantum cryptography, I would say there will be no quantum computing there. So you are basically coming with the classical version of the cryptography, which can outperform the quantum cryptography. So I don't know. I'm a person of quantum physics and quantum computing. And post-quantum cryptography, yeah, CS people would be the right people to reach, or you can just search on the net. Yeah, I'm not having anything on that. Yeah, Nielsen Chuang is a Bible for quantum computing. That is the Bible I said.
Okay. Any other questions, participants? Okay. Thank
David
you.
McMahon is a good book. Yeah, that's also a very good book.
Okay. 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 Thank you, Professor